Hey there, in this video I want to talk about the discrete cosine transform. The difference between the discrete cosine transform and the discrete Fourier transform is the underlying function. The Fourier transform uses complex exponentials and naturally will give you complex arrays as the result. The cosine transform uses cosines in place of the exponentials and guarantees that your result is real. You are limited, however, to starting with real values. You have to have a real array to begin with, and you get a real result to end with. Now, that's actually a pretty normal thing to run into in the real world. The other important difference between the Fourier transform and the cosine transform is what happens at the endpoints. So in the Fourier transform, if we have some kind of function like this, let's say our data looks like that, pretty wiggly. What the Fourier transform does, the discrete Fourier transform, is basically it's a Fourier series, so it pretends that the array is periodic, and it pretends it continues off to infinity, just duplicating itself. And so if we had something that was basically periodic to begin with, meaning like these two endpoints are at about the same height, it connects pretty well, and that would be a good place to use it. But what can happen here is, let's say our function looks like this, and then it gets duplicated quietly. It looks sort of like that. And so when we look at the function as it tries to fit it, it does something kind of like, let's just keep some low order terms. You got like these jumps here, which is not great. And that has to do with how it duplicated at the endpoint. So now the advantage of the cosine transform is what the cosine transform does when it duplicates our function is using the symmetry of cosines. Let's say it looked like this. What it's going to do is it's going to basically mirror image it around the endpoints. So we're going to get like this mirror imaging. And that kind of guarantees that it will, well, not kind of, it definitely guarantees it will be continuous. The downside is doing this assumes that you have zero slope at the ends, that your derivative is zero. And if it's not, you can also get weird terms sort of popping up out of the cosine transform, effectively making it look like there are frequencies that are more powerful than they actually are. So you don't just use cosine transforms blindly, but if you have something where the endpoints are not at the same height, it is a good choice as long as your data was real to begin with. Okay, so let's look at how it actually works. We're going to start with an array, and we'll just hard code this one to 8675309. And let's see what the DCT is. We can get to this from ffTpack.dct. Check our documentation in here. Okay, it wants an array. You might be used to ignoring everything else, but that would be a mistake here. Watch out here for this norm. So you've got none. Ortho, normalization mode, default is none. What's going on there? See the notes. Okay, I mean, they're really burying this for something that's actually super important. Okay, and when you get down into here, you can see it's talking about there are like different types of DCTs, type 1, type 2, type 3, type 4. What is going on? The one we want requires norm equals ortho. Otherwise otherwise it's weird. So we want to do always norm equals ortho, just like always. Just always do this. I don't even know why they wrote it the other way. So let's do that, and then we'll print the DCT just to see, you know, what does Jenny's phone number look like under a discrete cosine transform, because that's important. And then let's get our y again by doing the inverse. ffTpack.idct of the original DCT. We got to put in this norm equals ortho again, otherwise it's going to do weird stuff. And let's print what we get back. Okay, so first thing to notice, our transform here, our discrete cosine transforms all real, so no j's this time. And then when we transform back, you know, we are good within rounding error. So like the 0 here is now 10 to the minus 15, close enough. And since these are all real, they're nice for plotting. We don't have to worry about that absolute value business that we had with the Fourier transform. So we can just plot the DCT as is. You'll notice we also don't get any mirroring. We don't have like a Nyquist frequency anymore. We have to use all the values. And this has to do with storing information. So in this case, we started with an array that had 7 values in it, and we have to end with 7 values after we do the transform. And it's the only way to have enough information, 7 floats to get 7 floats. With the Fourier transform, if we started with something real, say we had 7 floats, let's make it an even number. Let's say we had 8 floats, and then we transform it into something complex. We only need 4 complex values because each complex value has 2 floats to it. And when you have odd values, you have the 1 extra point. That's basically your first point in the array. But in effect, you can throw away half your values or just under half your values, depending on if it's even or odd. Whereas with the cosine transform, we have to keep all of our values. So plot all of them. There is no cutoff halfway through. There is no weird mirroring effect. In many ways, this is the much more sane transform. The reason it's not the only one used is because it requires that your array definitely be real to begin with, and the endpoint business, where it assumes the slope at the endpoints is approaching 0. So it's not always the best thing to use, but there are places where it's better, maybe a little bit more sane than the Fourier transform. And if, what happens if we take away norm equals ortho? It's not the same. It's just kind of terrible. Oh, you know what? I never plotted it again. There we go. So the shape doesn't change, but the normalization is what changes. And so when we transform back, like this is not 8675309, even though I use the same Paul signature. Yeah, just always use norm equals ortho is like the big thing here with the discrete cosine transform.